All right, in this video I want to talk about two-column geometric proofs, the structure of thought behind them. And so what I'm going to teach you in this video is not taught in the textbook. You will not find it on any other videos. This is made by me so you can understand what is really going on behind a two-column proof. The first thing to understand is that all textbooks are different. They all have a lot of core theorems and postulates, but they have some different theorems and postulates as well. And so the textbook that you're using might have a different name for the same concept, or it might not have that theorem at all in your textbook. So for example, a common one today is something called linear pair postulate. But in some textbooks, it's called linear pair theorem. In the textbook I'm going to use, it was actually part of an older postulate called angle addition postulate. And so these all have the same meaning, but they have different reasons that would be provided in a different textbook. So make sure you understand that. The textbook I'm going to use today is my favorite one for geometric proofs. It's this one right here, Geometry by McDougall-Little Publishing Company. The authors are Jurgensen, Brown, and Jurgensen. It came out about 25, 30 years ago. I don't know exactly how long. I didn't look it up. But in my opinion, it teaches proofs, the actual thought of proofs, the best of all, high school, middle school geometry textbooks. It is still used today in some schools. In fact, one of the local schools here still uses it, Sunny Hills High School. They use this for their honors textbook. Okay, so in addition to that, we're going to talk about definitions. The thing that you have to understand about definitions is that every single definition is a biconditional. And why is this important? It's important because every proof is simply a collection of if-then statements. It's a big, long-running if-then statement, okay? And biconditionals actually have two if-then statements contained within them. So for example, I'll take a definition in this book. It's from page 13. It's the definition of congruent segments. And the definition says that they are segments that have equal lengths. Okay, so how do we do a biconditional? A biconditional means the following. If you would say if and only if, abbreviated as IFF commonly. If I say A, if and only if B, that's a biconditional, and it breaks down into two conditional statements. If A, then B, and if B, then A. These are the two statements. Well, every definition, you don't see it though. It doesn't say if and only if in it anywhere, so how does this work? It's still a biconditional. How? The first one will be if segments are congruent. Use, typically for the first version, version 1, use the definition word. So if segments are congruent, then they have equal lengths. And the second step is to reverse it now. You're just going to change these positions. It would be, you have to modify the grammar sum. So if segments have equal lengths, then they are congruent. Okay? So this is a definition broken into two different conditional statements. Every definition has this property. That'll be important going forward. The next thing I want to recommend that you do is that it's something that I made a while ago, particularly for this textbook when I was tutoring it a lot. It's to make a list of all of the theorems and postulates that appear in the book. And so if you look carefully, I've broken it up into columns. There's an if column here and a then column here. And you start from the very beginning, from chapter 1, and then you're going to go to ruler postulate and segment addition postulate. The if for this is B is between A and C. The then is the distance is equal to the absolute value of A minus B. It also results in AB plus BC equals AC. Okay, then you'll see what we just wrote. Definition of congruent segments is right here. It's got two versions, an A version, and you don't have to write all the words. You can just say if congruent. So basically, what's congruent? Well, what do you think? The segments, right? So if segments are congruent, then they have equal lengths, and the B version is if equal lengths, then they are congruent, right? And so you'll do this. I did it for the first 3 chapters of the book. So chapter 2 is here, and you just make a list of all of these if-then properties, theorems, from definitions, theorems, and postulates. All of them, put it on there. Keep a running tabulation as you go through the book, and you're going to refer to it whenever you have a proof. Let's look at a proof now. I'm going to pause the video and then I'll start in a second. Okay, so returning back, first proof that we're going to do comes from page 39, example 3. The given is that the measure, some books you don't have to put this in. I think most textbooks you do. If you're talking about the numerical value of the angle's measure. If you're talking about the angle itself, angle AOC, then that's like an object. Objects you use the symbol congruent for. Measures like numbers, you use measure of angle AOC. That's the difference for that. Okay, so given that angle AOC's measure is equal to BOD's measure, it wants us to prove the measure of angle 1 equals the measure of angle 3. So how do we think about proofs? It's really quite simple. You just think about if-then. And the if that you're going to use is always based on what you know. When you're starting a proof off, you usually only know 2 things. The picture, if one is given, and the given statements. There could be more than one. You don't have to use all the givens in your first statement. You can, but sometimes it's better structurally to split them up for various reasons, which we'll cover later. Okay, so all we know is this picture, and what do we see in this picture? We can see that there's an angle 1, 2, and 3, and we want to talk about how angle 1 and 3 need to become equal. So we should probably try to introduce them using what we're given. We're given AOC. Well, AOC is here. What does AOC consist of? It consists of 2 angles, 1 and 2. So we should think if the picture is true, then what can I say? I can say, based on angle addition postulate, if you look here where my finger is, that it shows if the angle B or if point B is on the interior of angle AOC, then the measure of AOB plus BOC equals AOC. Okay, so we can do that here. This is exactly what we have. When we have a picture that looks like this and there's angles involved, and you want to either break an angle up or combine 2 angles, you should consider using angle addition postulate. And so the then would be what you write on the next line, right? And so we're going to say, basically, if the picture is true, then the measure of angle AOC is equal to the measure of angle 1 plus the measure of angle 2. And the reason is angle addition postulate. Different teachers have different shortcuts that you can write. This one was acceptable for some teachers around here. Maybe you have to write the word angle or something like that, or AAP. Okay, so then what I like to write underneath step 2 is in parentheses right here. This is the part you won't find in textbooks. I like to write what it was based on. It was based on the picture. It was not based. It's not that because AOC is equal to BOD's measure that AOC equals 1 and 2. That's not why we were allowed to write this. It's not like anytime 2 angles are equal, I get to break an angle up into 2 smaller angles. That doesn't make any sense. So it's not based on the given. Okay? It's based on the picture. The picture can be used more than once. In fact, we're also going to do 2 steps in one. We're also going to say measure of angle BOD, the other thing that was introduced in the given, is equal to measure of angle 2 plus measure of angle 3. As long as the two statements have the same reason, you can go ahead and write them both in the same step. Again, not true for all teachers. Some teachers want you to split it into 2 steps. That's up to your school and your teacher. Okay, so step 3 then. What can we say now? The idea is that as we go forward in a proof, every single statement has to be used as an if statement at least once. Except for one statement, that's the last statement of the proof. So when we look at the next one, we again have an if-then. It's if this is true, and if this is true, then what can we do? If I know both step 1 is true and step 2 is true, what can I say? And what I say would go in the then statement, right? It's if these two things, then step 3. And what will step 3 be? Well, think about it. If you've got AOC here and you know AOC is 1 plus 2, you can replace it with 1 plus 2. You can say measure of angle 1 plus measure of angle 2 equals BOD, which is also written here as measure of angle 2 plus measure of angle 3. So what did we just do? You can kind of visualize it, right? We crossed out AOC and replaced it. What does that mean if you cross out something and replace it? It's substitution. Substitution, property of equality. And there's a property of congruence as well. Some teachers don't make you write the property of equality part. Some teachers do. You'll have to know what your teacher expects of you. Okay, so once this then statement has been written, once we've written it, it's performed its function as an if-then, it now becomes an if statement for a future step. Okay, so what was 3 based on? It was based on 1 and 2. So again, we're kind of diagramming the background, the structure of the proof itself behind the scenes. What's really supporting these steps? This tells me that steps 1 was used and step 2 was both used to make step 3. So when we go to step 4, it's not likely, like 99% of the time you won't reuse these. Sometimes you will, but most of the time you won't for most proofs. Most of the time we're just going to use this. Okay, and so we had to have the given first and then this, but you actually could have switched steps 1 and 2 because they don't depend on each other, right? But before we could write step 3, we had to have steps 1 and 2. Both had to be in place in order to use substitution. We had to have an equation that we're substituting into, and we had to have a statement about what's being substituted in. So we go to step 4 and we've already used 1 and 2, then 3 becomes the if. Or does it? If there's nothing that you can see that you can do right away with this, you might have to add one other step that's not really based on anything. We can kind of call it a given, if you will, but it's not really stated up here. And it's that what we want this, right? We want measure of angle 1 equal to measure of angle 3, and we have a measure of angle 1 here and a measure of angle 3 here, and the equal sign. The only problem is these two measure of angle 2's. So think about your ending and what you're trying to get to and look at where you're at. I would like it if these measure of angle 2's went away. Now, if this was an equation, you could say something like a plus b equals b plus c, and you would now subtract b from both sides if it had numbers and stuff. But with geometry, it's usually true for most teachers. They want you to state that measure of angle 2 is actually equal to measure of angle 2. Even though it's kind of obvious in your mind, in a proof you usually have to state it. I don't know many teachers that don't make you show this 4th step. And then the reason that you would give, whenever you say something is equal to itself, it's reflexive property. And if you're using congruent symbol, it's of congruence. If you're using an equal symbol, it's of equality. So reflexive property of equality. Why is it not symmetric? Symmetric actually is an if-then statement. It's that if A equals B, then B equals A. It switches the order. It's two different things that are equal that I can switch the order of. Reflexive is when the same thing equals itself. Okay, So now what? What was step 4 based on? I'm just going to put an R for reflexive property. Just something that we'll put there. So it didn't use step 3. We thought about step 3 when we made it, but we didn't actually use step 3 as an if statement. Now we get to the next step, step 5. And again, because I've said these things are equal now, I can now take them away from this. Let's write the format. It's if measure of angle 1 plus measure of angle 2 equals measure of angle 2 plus measure of angle 3, and measure of angle 2 equals measure of angle 2. If both of those things are true, then I can take away the measure of angle 2 from both sides. And so now you will get measure of angle 1 equals measure of angle 3. And what did we do here in this simplistic example? We subtracted something. So if you subtracted, that's a hint at what you're doing. That will be subtraction property of equality. And that uses both steps 3 and 4. They were both needed. I couldn't make step 5 unless I had both 3 and 4. So it's if this, nothing happens yet, then I can write this because of the picture. If both of these are true, we could write step 3. If step 3 and 4 is both true, we can write step 5. So then when you get to the end, the thing that you're trying to prove, you will not use it in an if-then statement. It is the final then statement, and you're done. Okay, let's go to the next proof to show more how this works. Okay, this is going to be the second example for this video. We're going to talk again about diagramming a proof and what that means and how it will help us work through proofs without having as much difficulty. So we have one from page 59 of the earlier mentioned textbook, problem number 13. It says, given that ray OA is perpendicular to ray OC, so this is 90 degrees, prove that angle AOB and angle BOC are complementary angles. So we have statements and reasons, and first statement is already here. In general, like 99% of the time, your first statement will always be the given or one of the givens if there's multiple given pieces of information. Okay, so how do we progress? Well, we just have to think, what is the defined thing in this statement? The defined thing is the word perpendicular. Rays, or there may be a special term, but we kind of more care about this perpendicular word. What does it mean for segments or lines to be perpendicular? The first thing that we should go to is we should look at the definition, right? The definition of the word. Always go there first. And so again, on this sheet of paper that I made, I will show it to the camera now. Definition of perpendicular lines is the top of this page. There's two versions because we said that definitions are biconditionals. All of them have two versions. And the first one says, basically, if lines are perpendicular, then the measure of their angle is 90 degrees. And then the second version is, if I know the measure of an angle is 90 degrees, then I can say that it is perpendicular. You can also, instead of saying the measure of the angle is 90, you can just say it's a right angle if that's going to benefit you more for the proof that you're in. The one that we're going to use for this problem is we're going to use that the measure of the angle equals 90. Okay, so then we're going to write that next. And how do we know that it's equal to 90? It's because of the perpendicular. Again, every statement in a proof, every line that goes over here is an if-then statement. And it will either be if a previous step, then the next step that you're on, or if this picture, then something else based on the picture. So we can say that the measure of angle AOC is equal to 90 degrees. And this would be the definition of perpendicular lines. In particular, it's the first version, the A version of the one I showed you a minute ago. And again, I like to put underneath the 2 a 1 in parentheses to indicate this was now used as an if statement. Now we just made step 2 when we wrote the reason here. We've now used it as a then statement. This was a then statement. It's if this, then this. But now what happens? Now we're going to have to look to something else to use. Instead of step 1, you could use perpendicular again in some proofs, but it's very rare. Again, so we go to step 3. Now, the fact that AOC is 90 degrees, does that lead us to any new special conclusions? Not really. There's not a whole lot you can do with knowing that an angle is 90 degrees. So instead we should look at the picture and also look at what we're trying to prove. We're trying to prove that AOB and BOC, that's this angle and this angle, are complementary angles. Well, if you want to have these things proved, then you should introduce them to the proof at some point. How are we going to introduce AOB and BOC to the proof when the only thing we've talked about so far is AOC? Well, that leads us to think about angle addition postulate. An angle addition postulate can take two smaller angles of a larger angle and combine them to make the larger angle. So you will now say the measure of angle AOB plus the measure of angle BOC is equal to the measure of angle AOC. And this is based on the picture. It's because B is in the interior of angle AOC, which if you look at angle addition postulate, I'm not going to show it, we showed it in the last proof, that's one of the things that you need to have. And once that's true, then this is true. So 3 is not based on step 2. It's not because AOC is 90 that this is true. This is not the if portion of this then statement. Instead, it's if this is what the picture looks like. So if picture, then step 3. I'm not going to write it all out to save time. Okay, so the step 3 is now a then statement. Okay, and what's the justification? It's angle addition postulate. Angle addition postulate. So we go to step 4, and as you're doing this, you should notice that you're building up unused statements. What does it mean to be unused? It means it has not become an if statement yet. Okay? And if it hasn't become an if statement, the more of these you build up, the more you kind of need to use them. Okay? So now we want to look at this and ask ourselves, is there anything I can combine with this piece of information and this piece of information? Well, this talks about measure of angle AOC, and this talks about measure of angle AOC. And since this is 90, well, I can just replace this with 90. So it's measure of angle AOB plus the measure of angle BOC is equal to 90. And you would call this what? What did we do? We replaced something. This is the replacement equation. We replaced it with what that thing was equal to. It was equal to 90. So we're going to call it substitution property of equality because we're using equal signs. Now, what's interesting to note is that technically this could also be transitive property. In the last proof, you couldn't do transitive property. In fact, some teachers are real sticklers and they'll force you to use transitive property whenever you have it to use. I think that for most teachers, though, that's not a requirement. If this works and it is acceptable to do substitution, it's okay, but you should know that transitive is also acceptable and by some teachers even preferred in this situation. Again, transitive is the one where if A equals B and B equals C, you'll kind of see a Z. A to B to B to C. Transitive is the way I think of it. So then it's like a chain connecting A to B to B to C. That's when you can use transitive. How is this transitive? It's this to AOC to AOC to 90. That's how it's transitive. Okay? So we're going to stick with this reason though. So 4 is based on both steps 2 and 3. So in parentheses, I will put 2 and 3 underneath the 4 to let myself know, or somebody else if they know this technique, that these were what I used to generate step 4. It's because of these steps that step 4 is allowed to enter the proof. It's if steps 2 and 3, then step 4. So now what do? Well, we need to go to step 5, and again, if you haven't used step 4, you should think about using it. Well, what are we trying to prove again? We're trying to prove that AOB and BOC are complementary angles. Then we should probably look up the definition of complementary angles because that's the defined term. And I have it on my second page for chapter 2 of this book. You will see that it is right here, definition right here, this finger, definition of complementary angles, and it shows that the if portion is if angles are complementary, then the measure of those angles adds up to 90. Now that's not the version that we want. Why? That version requires us to know that they're complementary, right? Technically, your teacher's not going to know if you didn't know which version you were using, but you should know so that you understand the proof more. So if we go back to definition of complementary angles, there's a B version right here, and it's if the measure of two angles adds up to 90, then those angles are complementary. That is the very definition. It's version B, and we can now say what we were trying to prove, that angle AOB and angle BOC are complementary angles. You can abbreviate complementary COMP for most teachers. And since we use the definition, that's the reason. Definition of complementary angles. Notice that step 5 uses step 4. These little X's mean that that step got used as an if statement. So because we use step 4, we put an X next to it. At the end of your proof, every step except for the last one should have a little X next to it. That's when you know you've done it correctly, because all of these things have led us to conclude what we were trying to prove, which is always where the proof ends. Going to go to the next example.